Alright guys, this is 5.2, definite integrals. An integral is essentially the opposite of a derivative. Up to now, we've pretty much been doing derivatives. Now we're going to change gears and do the second half of calculus, which when the A, B, C would be the B. A is derivatives, B is integrals, and C winds up being the series stuff. It says in the last section we found the area under a curve by finding the area of a finite number of rectangles, LRAM, RRAM, and MRAM, or a finite number of trapezoids. Every one of these was an example of what is called a Riemann sum. We're going to stick for rectangles for the time being. Okay. It says the following steps illustrate what has to happen to be considered a Riemann sum. I will let you read that at your own time. Essentially, though, what all this is saying is on any picture from A to B, to find the area under the curve, you simply make a whole bunch of little rectangles and add them up. And if you'll remember from yesterday, that the more rectangles you have, the closer it approximates the area. So what actually happens is as the number of rectangles goes to infinity, it is the area. Because if you'll look right here at 100 rectangles, the exact area is 81.667. At 100 rectangles, you've approximated it to within 1. It's 80.794. The more rectangles you have, the closer you are to the actual area. And if you look at your midpoint, it's actually to 2 decimal places. It's accurate to 2 decimal places. The right Riemann sum is going to over-approximate just a little bit, and then the trapezoids is also accurate to 2 decimal places. So I'm going to skip over. A lot of this is notation. It's just explaining where the integral comes from. Basically what an integral is saying that as the number of, and this is just like what, just skip over that. Alright, here we go. As the number of rectangles from A to B goes to infinity, as I make all these rectangles, in other words, the limit as n approaches infinity, this is the sum. That's summation. And this is what was on that other page. K equals 1 to 8 to n number of rectangles of f of c k times delta x. All that is a bunch of notation that says as the number of rectangles goes to infinity, it makes the area. So that's this little integral sign is pretty much the sum. It's saying this is the area under the curve from A to B of f of x. That's all it's wanting you to do. So when you see the integral, it's just saying this is my lower bound, this is my upper bound, and I want to find the area under the curve. It says important. If you want to read all that up above, be my guest, or if you want to really see what's going on, go watch Mr. Leckie. I'll put a link to him as well, because it's just the definition of the integral. And all that notation is just confusing, so we're just going to skip over that and start working problems. It says use definite integrals as area. We can define the area under the curve of f of x from a to b as an integral from a to b, as long as the curve is non-negative and integrable on the closed interval a to b. It says for each of the following examples, sketch a graph of the function, shade the area you're trying to find, then use geometric formulas to evaluate each integral. So this is, I want to find the area under the curve from 2 to 9. I'm going to draw a picture. From 2 to 9, and my function, f of x, is equal to 3. So 1, 2, 3, it's just a line. Okay, so I want to find the area from 2 to 9. Well, it's a rectangle. I have made a rectangle here. So to find the area, I just do length, be 7, times width, which is 3. 7 times 3 is 21. So the integral from 2 to 9 of 3 is 21. I want to do the integral of the absolute value of x from negative 1 to 2. From negative 2 to 1, I'm sorry. Negative 2, 1. Absolute value is shaped like a V. So I've got two little bitty rectangles, here and here. The area of a rectangle is 1/2 base times height. So my base is 2. My height, if I fill in negative 2, absolute value of negative 2 is 2, so it's 2. So it's 1/2 base times height plus the other triangle is 1/2. The base is 1, the height is 1, so it's 1/2 base times height. So 4 times 1/2 of 4 is 2, plus half of 1 is 1/2. 2 plus 1/2 is 2 1/2. The square root of 9 minus x squared is a semicircle, and I want to go from negative 3 to 3. Well, that just so happens to be where it's at. And I want to find the area under the curve. And it's actually, we say area under the curve, but it's the area between the curve and the x-axis. You can't have a negative area. This is a semicircle. From negative 3 to 3 is just pi r squared would be an entire circle, but this is half of a circle. R is 3, so it's 1/2 pi 3 squared. So it's 1/2 pi 9, so 9/2 pi. And that's the area, so it equals 9/2 pi. Okay, it says consider the function 3 minus x. 3 minus x could also be written as negative x plus 3. M is negative 1, B is 3. So I begin at 3, and I go down 1 over 1, down 1 over 1, down 1 over 1, down 1 over 1, down 1 over 1. I'm actually going to have to keep going. 4, 5, 6, 7, 8. Down 1 over 1, down 1 over 1, down 1 over 1. In retrospect, I probably should have put a graph. Oh well. It says sketch a graph. What is the area between the curve and the x-axis between x equals 4 and x equals 8? Okay. So from 4, 1, 2, 3, 4, to 8, 5, 6, 7, 8. Okay. That has made a trapezoid. And we learned in the last section that a trapezoid, the area of a trapezoid is 1/2 the base, I'm just kidding, 1/2 the height times B1 plus B2. Well, the height of my rectangle, or trapezoid, is 4. And then my first base looks like it's down 1. And my second base is down 1, 2, 3, 4, 5. Yeah, this would have been much better had I done a graph. So it's 1/2 times 4 times 6. So 2 times 6, so it's 12. An area is always positive. I think that just goes against what I said a minute ago. I mean, you could say have a negative integral, but you can't have a negative area. It says evaluate the integral from 4 to 8 of 3 minus x. It is negative 12 because it is below the x-axis. If the area is below the x-axis, it's a negative integral. If it's above the x-axis, it's a positive integral. It says given 0 to pi of sine of x dx equals 2. Use what you know about a sine function to evaluate the following integrals. So let's do a little sketch. of our sine graph. We know sine starts in the sand, and we're going to pi. Well, there's pi over 2, pi. Yeah, let's start over and draw it down here where we can see the whole thing. Because it's going, if I look at my problems, I need to go all the way out to 2 pi, and I need to go all the way back to negative pi. So here's negative pi. 1, 2, 3, 4. 2 pi. Pi. Sine starts in the sand, and it goes up to 1, down to negative 1. Here's my sine graph. And I'm actually going to be using this a bunch, so I'm going to copy and paste it. No, not the whole thing. No. No. Copy. Okay. Okay. Use what you know about a sine function to evaluate the following integrals. So pasting my thingy right here, I want to pull it up there. It told me that the area under the curve from 0 to 2 pi, from 0 to pi, is 2. Okay? I want the integral from pi to 2 pi. Well, if that's 2, this piece is the same. So but it's below the x-axis. So it's actually going to be negative 2. And it's actually a positive area. It's just because it's below the x-axis, it's negative. Alright, I'm going to paste this in again, right there. So again, remember, this is 2.
Roger Gist, if you're in the building, please come to the front. Your ride is here. Roger Gist, if you are in the building, please come to the front. Your ride is here.
Thanks, Mr. Green, for interrupting my video. This is also 2, but it's technically a negative 2. So I've got a positive 2 plus a negative 2, so it would be 0, because the area above cancels out with the area below. Alright, let's do it again. Paste, no. Paste, no. Paste. I'm struggling. There we go. This one is from 0 to pi over 2. Well, if from 0 to pi is 2, the whole thing's 2, what about pi over 2? Well, if the whole thing's 2 and you cut it in half, it would be 1. Alright, again. Really? I'm getting mad at this. Let me just go ahead and do it now. Paste. Okay. From negative pi to pi would be from negative pi to pi. Now you've got, this is essentially negative 2 and this is 2, so negative 2 plus 2 is 0. And then 2 plus sine of x, this one's a little tricky because you have to move it up 2. This would be, if I added in extra stuff here. Whoops, I'm kidding. Hold on, that's horrible. And I said, here's my x-axis. X. Y. I want the area under the curve from 0 to pi. So what have we essentially made? We've made a rectangle that has a width of pi and a length of 2. So what's the area of that? 2 times pi is 2 pi. And then the area up here we know is 2. So it would be 2 plus 2 pi. That one's tricky. And then it says, by this point, hopefully you understand the following concepts. The limit of a Riemann sum is used to define a definite integral. A definite integral can be used to find the area under a curve if the curve is above the x-axis, and if the curve is below the x-axis, the value of the definite integral is negative area, even though no one in their right mind would ever actually use that phrase in a math class if they wanted to be taken seriously. Since the definite integral can be thought of as area, you can draw a picture and use geometric formulas to find the areas. But what happens if you were asked right now, this instant today, to find the definite integral of a function that doesn't lend itself to nice geometric shapes? The good news for you is you don't even have to worry about how to do these by hand yet. You get to use your calculator. So we're going to look at how to use our calculator to do these. So hopefully you can see all this. If you're doing this on your phone, it's going to be teeny tiny. No, I don't want to save anything. I'm going to go to a calculator screen. It says evaluate from 1 to 3 of x squared minus 2x plus 2 dx. So, I hit menu, I go to calculus, I go to integral, and from 1 to 3 of x squared minus 2x plus 2 dx, and I hit enter. 14/3. Oops. And just in case you couldn't see that, there it is. I'll just do it this way. I'll just kind of go back and forth. I'm not sure what just happened. Okay, 14/3. So the next one is 3 plus, I'm just going to keep flipping back, 3 plus 2, the integral, menu, and the other way to do it, hold on, there's another way, is to hit control, nope, no control, just this little book right here, and let me go to the calculator that most of us have. It's right here, this little button, and the integral is right there. 3 plus 2, the integral from 0 to pi over 3 of tan of x dx. 2 natural log of 2 plus 3. Approximately, if it was on the calculator part, and it would be, 4.386. So either 2 natural log of 2 plus 3 or 4.386. And then the last one is the integral, so from 1 to 8, I forgot I had my paper sitting here, I could have been looking at it the whole time, square root of x dx. Ooh, I want a decimal. 14.418. And that's it. That concludes this lesson. Basically, what you should have got out of that is you can use the area to approximate the integral. And for right now, you can use your calculator. The end.